Imagine you're a bug on top of a spinning pizza. You're not sliding off, you're just going in circles around the center of the slice. This is called pure rotation. And every single point on the pizza, so every section of the crust, every piece of pepperoni, every topping, they're all spinning and traveling in a circle around the same center. This center is what we call the axis of rotation. And to see how far you've spun in a certain amount of time, we use an angle. So the amount the angle changed is how far you traveled. This is called angular displacement. So for example, when you look at a clock and you look at the clock hands, you don't measure how far you moved in centimeters, you moved how much you've turned. Physics runs on something called radians, and radians are a substitution for degrees. So for example, 360 degrees is equal to 2 pi in radians. If you don't know what radians are or you don't know why we use them, it's in the description. Very briefly, so that you can still study from this video, I'll explain what radians are. The definition of 1 radian is equal to when the arc length traveled is that of the radius. What does that mean? Let's say you're a hamster and you're running on a hamster wheel. When the distance you've ran is equal to the distance of the radius, then you have turned 1 radian. And so here are the formulas that we're going to be using today. The angle you've turned is equal to L over R. And this L is arc length. This R is radius. This formula has a variation, so when you rearrange it, you can get this. Arc length is equal to radius times the angle. Let's go through a quick example to put some of these ideas together. So a car tire, let's say you have a car, looks like this. A car tire, it rotates 10.5 revolutions. So it spins 10.5 full circles. What is this in radians? Well, let's see. Since 1 revolution is 360 degrees, and 360 degrees is 2 pi in radians, let's multiply 2 pi by 10.5. This is roughly 66 radians. Here's a second example. So let's say you have an F-22 fighter jet. This is a famous fighter jet from the US military. And this fighter jet, it's 500 meters up in the sky. And it's moving at the speed of sound. Your targeting system on board of this fighter jet subtends an angle of 0.0015 radians. What does subtend mean? Subtend means it covers this angle. So, in simple English, your targeting system on your airplane, the angle covered, so this angle that it can see on the ground is this. And this length of how far it can see on the ground is how big an object it can lock onto. Now we have a formula for this, which we just wrote down, which is radius times the angle. The radius is 500 meters, right? That's the distance. Because really, we can imagine this as a big circle. Just looking at one portion. So 500 meters is the radius. And the angle is given here. And that's 0.015 radians. This is equal to 0.75 meters. So the smallest object it's able to detect is something this big. It's 75 centimeters long if you are 500 meters up. Because of the way this formula works, the further up you are, the larger the object has to be to subtend the exact same angle. Now for the main part of this video. To describe rotational motion, we use angular quantities. For example, angular velocity and angular acceleration. What are these? Let's go through the first one, angular displacement, which is how much did you rotate. If a wheel turns from angle position 1 to angle position 2, this change in angle is the angle at the second position subtracted by the angle in the first position. It's just like displacement in linear motion, right? The final position minus the initial position is the same thing but in angles. So that's angular displacement. How about the second angular quantity? It's angular velocity. So how fast are you rotating? Just like linear velocity is displacement over time. And by the way, if you don't know, this delta means change in. So change in position divided by change in time. Just like how we have this for linear motion, circular motion has angular velocity, which we denote with this W looking symbol. Angular velocity is equal to angular displacement divided by a change in time. And instead of, usually we have things like meters per second. For angular velocity, we have radians per second. It's how many radians you're traveling every second, how fast you're rotating. And every single point on a circle, so no matter how far you are from the center, every single point has the exact same angular velocity, but the linear speed is different. We're going to look into this soon. And here's a third one, and this one's very important. It's angular acceleration. So in linear acceleration, we just denote with A, but angular acceleration is denoted with a fancier looking A, which usually looks something like this. You can Google it. There's different ways to write it. And just like how linear acceleration is given with change in velocity over change in time, angular acceleration is change in angular velocity divided by change in time. So you might have noticed a pattern. All these rotational kinematic quantities are just like the linear counterpart, but in terms of rotation. It's the same flavor as linear acceleration, just in rotation. Now, do you remember when I mentioned that angular velocity is the same no matter how far you are from the center? But linear velocity is not. How does that work? Let me try and explain this to you with an example. Imagine you're on a merry-go-round and there's two horses. The first horse is this far from the center. The second horse, horse B, travels along the edge. Every object rotating around the axis of rotation traces out a circle, right? That's the path they follow. And the radius for A is shorter than the radius for B. But here's the key thing. They both make one full rotation in the same amount of time. But B has, it's technically traveled more distance, right? Because it's a larger circle. So the linear velocity is different because B has to travel longer linear distance in the same amount of time. But the angle that they cover in this amount of time, 360 degrees, is the same. So the angular velocity is equal, no matter where you are on the circle. So it's two different points. They move at different speeds, but they rotate the same angle. And this will make sense when we go through some problems later on. And there's a formula that connects linear speed with angular speed. And what is this formula? It's V equals radius times angular velocity. There's going to be a lot of formulas in this topic, which is rotational motion. It's a very big topic. It's very important on things like exams. So there's a free cheat sheet that you can grab in the description. It has every formula you'll need for this topic. Let's go through another concept. It's tangential versus radial acceleration. And we went through this already in my circular motion gravitation videos. But to sum it up, tangential acceleration looks like this, right? It's tangential to the circular path. For example, if you had a circular platform and you wanted to spin it with rockets, you could have 4 tangential rockets boosting it like this, and it would end up spinning because of the tangential acceleration. What's radial acceleration? Radial acceleration, also known as centripetal acceleration. Here's a brief refresher. The formula is velocity squared over radius. And this can also be written as angular velocity squared multiplied by radius. And centripetal acceleration is how hard you're getting pulled toward the center. Because since you're always experiencing centripetal acceleration, that's what keeps you on your circular path, because you're always getting pulled toward the center. So if angular speed is increasing, radial acceleration pulls you in, tangential acceleration keeps you moving around the edge. And this forms a vector triangle. That would be your total linear acceleration. And if you don't understand these vectors, I made a full masterclass for it for free on this channel. Very important. Vectors are everywhere in physics. And if you're fast at vectors, physics is very easy. Let's go through a proper problem now. Imagine you're a NASA scientist and there's a futuristic gravitational simulation ring. or astronaut training, and it starts at rest. So let's visualize this. It starts at rest, which is 0 radians per second. And the astronaut sits here, 3.2 meters away from the center. You are tracking, after 6 seconds, you're tracking two things. The first thing you want to find is the angular velocity after 6 seconds. And let's say the angular acceleration is 1.5 radians per second squared. So angular velocity after 6 seconds. The second value you're tracking is linear velocity. Let's go ahead and solve this together step by step. So the first thing we have to understand, what formulas we got to use. Here's something special about rotational motion. If you remember all the way back in 1D kinematics and the kinematic equations, we can actually use them for rotational motion. I'll show you. We're looking for angular velocity, and we have two values. We have the acceleration, and we also have the time. What's unknown is this, the velocity after 6 seconds. Let's find a formula that links it up. If you remember from 1D kinematics, there's a formula that looks something like this. Velocity is equal to initial velocity plus acceleration multiplied by time. We can rewrite this in terms of rotation, and it looks like this. And it does the exact same thing. So let's plug in our values. Angular velocity was 0, right? Because it starts at rest. Here's the acceleration, and here is the time. We get 9 radians per second. Cool. Let's find the linear velocity now, because that's the second thing we're tracking as a NASA scientist. Linear velocity is given with this formula, if you remember. I did mention it briefly. And what's angular velocity? That's exactly what we just found, which was 9 radians per second. So let's plug this in. Multiply these two values. We get 28.8 meters per second. By the way, that is insanely fast. So whatever astronaut is doing this training, clearly very hardworking. This is the last section of the video. And it's not too important, but you should know it. It's frequency and periods. So the big picture idea is that frequency is how many spins per second. And angular velocity is how much angle you're sweeping through every second. Now we can connect these two ideas. Because one full revolution is equal to 2 pi radians, angular velocity can be found with 2 pi multiplied by frequency. And frequency can be found with angular velocity divided by 2 pi. Why does this work though? Let's say your frequency is 4 spins every second. Your angular velocity would be a full revolution times 4. That would be how fast you're going. What's time and periods? Well, a period is 1 over f. And it's exactly how much time it takes to do one revolution. So let's say you spin 4 times per second. Then your time is 1 over 4 seconds. Spin duration. For every topic I cover, I like to create a free cheat sheet. And I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.